Here is an introduction to Milky Way formation to accompany chapter 25 of the textbook Astronomy from Open Stax. So what we're trying to describe here is, we're trying to explain is how did our Milky Way end up with the structure that it has. So there was another lecture that we had on the Milky Way structure, and so you know that there's a bulge and sort of a bar at the center of the Milky Way. There are these spiral arms. There's a thinner disk, a thicker disk, and then this halo of stars. So it's a pretty interesting structure. How do you get there? And let's try to cover how that came to be. So let's start out with the formation of the disk. So you initially have some clouds of gas out in the universe, and you're going to have some fluctuations in the density distribution, right? So you can see this looking at the cosmic microwave background that we looked at in the Introduction to Big Bang lecture. There are some regions of higher density, and so that higher density means that gravity is going to cause that region to collapse. And the particles within our gas cloud, these are going to have some random motion, right? So this particle maybe is moving that way, that one that way. And if you add up all the motion of these, it's extremely unlikely that, for instance, all the rightward motion is going to cancel out with all the leftward motion. Right? There's going to be some net movement here, and that just means that there's going to be some net rotation. This cloud, if you take any random cloud of gas in space and it starts to collapse, it's going to wind up rotating because things would have to just be absolutely perfect for it not to. But then as the gas particles collide, what's going to happen is they're going to tend to favor a particular direction, and that's the direction of rotation. And you could think of if you were in a stampede of horses and you were trying to run or ride a horse through this stampede, it's going to be a lot easier to just go with the flow than it is to go against it. So basically, as time goes on, you're going to have fewer collisions and gentler collisions. So things are going to start to kind of orbit in the same sort of way. And so then if after a long time, your overdensity of gas is going to wind up being something kind of in a disk shape that is then rotating. Now you might wonder, last time we talked about Milky Way structure, there's a dark matter halo that's like a sphere, this spherical blob surrounding our galaxy, or really encompassing our galaxy. And you might wonder, well, wait a second, why is that not in a disk? Because the dark matter would collapse too, right? So why doesn't this same process happen? And the reason is that these collisions that we're talking about, these are what you may call a contact interaction, but it's really electromagnetic interactions are pretty much what is causing collisions. So when we have two like charges repel each other, for instance, that's a virtual photon exchange that is mediating that process. And dark matter, by definition, is dark, and so there's no photon interactions with it. So basically, it doesn't really collide with itself, and so there aren't going to be these collisions that you need to get a disk formation. So that's why your dark matter still sits around as a sphere. And if that sounds like hocus pocus to you, we can actually see the same kind of thing happen in young stellar systems. And this is also the kind of thing that explains planetary systems like our solar system, where you have the sun, which you can kind of think of as the galactic bulge, and then the planets orbiting, which you can kind of think of as the disk. And we'll talk more about that in the stellar and planetary formation set of lectures. Now, to be clear, there can still be sort of spherical clumps of stars out there. So there are these things called globular clusters that we'll talk more about in a moment. And this is a conglomeration of stars in kind of a sort of spherical thing, maybe more at the center. This can still happen. And the reason is that stars don't collide very frequently. So once you get some stars kind of near each other, they can be in this blob, and they're not really going to ever collide. So it's not like you have stars colliding to form a disk. they're more or less never going to interact. So this little spherical thing of stars can still exist. Now you have your collapsing gas cloud forming a disk. What about star and star cluster formation? How does this happen? And this is the same idea as the collapse of the initial gas cloud to form the galaxy. You have local regions of overdensity. So what's shown here is a image of a place in our galaxy that has a lot of star formation going on. The color here is, for our purposes, essentially related to the density, and the different boxes that have numbers, you can look at the detailed picture of that by going to these other panels. So for instance, this square 2, we zoom in and we see a cluster there, and there are just lots of these things. So again, you basically just have sort of overdense regions of higher density in the early Milky Way, and those can clump to form stars. And I mentioned here that this is happening now. We can see this occurring. Again, these are globular clusters. So what about the spiral structure formation? How does that come about? Because we've explained kind of the existence of a disk, but the Milky Way has these spiral arms. So if you have an object orbiting a central point, there's going to be the force of gravity pulling inwards, and effective force, the centrifugal force that feels like it's pulling outwards. So this is just like you feel, for instance, on a roller coaster when you go over a hill. You feel something sort of pulling you downwards, and also gravity's, or you feel like you're being pulled outwards out of the roller coaster seat, and gravity's pulling you downwards. Same kind of thing. So you have these two forces sort of fighting each other. So when you set these two equal to each other, and you solve this, which you can do in Physics 2001 if you take that algebra-based introductory physics, and you come up with something called Kepler's third law. We don't need the equation right now, just what we need to know is that objects that are further out from some central body that they're orbiting, those are going to move a bit slower than objects that are orbiting at a closer radius or in a tighter circle. And so this is going to produce, differential rotation. So what we mean by differential rotation is that your orbiting speed depends on the radius. It's not fixed. So for example, let's say we have these two clumps of gas here for simplicity, and there's a general rotation in the clockwise direction. The stuff that's closer in is going to orbit faster than the stuff that's further out from Kepler's third law. And so as the rotation begins, there's going to be more progress made in the center region, or in the central region, than there is in the outer region. So this stuff at a larger radius more or less hasn't moved. The stuff at an inner radius has moved a lot, and there's everything in between. And so then as the rotation continues, you're naturally going to stretch out into these sort of spiral structures. The problem is this will also destroy them, right? So if you think about it, this is just going to, these spirals are just going to wind in on themselves, and this is something that was known as the winding problem. Like, you destroy the spirals pretty quickly. You could say, well, perhaps the Milky Way and other spiral galaxies we see are just in this sort of sweet spot, but that doesn't fit with galaxy formation timescales and galaxy rotation timescales, so that probably is not the explanation. So one possible explanation is that you have these streams of gas. These have higher density, so that's where you're going to have star formation. When you form a star, it emits photons, and that's a kind of a stellar wind. So that's blowing off photons. It's going to push material away. And also, those stars will die, undergo stellar explosions, and again, there'll be this big thing of shock wave of photons pushing outward. It's going to shuffle matter around. And that, in principle, could maintain these spiral structures. So you get the gas in these kind of spirals, stars form, and then they're basically kind of clearing matter out in between from the act of star formation and star death. That could be the case. An alternative theory is something known as the density wave theory. And the idea here is that the spiral arms themselves aren't necessarily consistent groups of stars. So it's not like a carpool scenario where all of these are just a group of stars and they're riding together the whole time. It could be instead that there are regions with higher density and stars basically are moving in and out. So you have stars orbiting the galaxy and they spend some time, extra time in the higher density regions due to gravitational interactions, and they spend less time in between. And so it's kind of like imagining these spiral arms are like stoplights in town. So your stars are driving around the roads, they come to a stoplight and they wait, and then the light turns green and then they go onwards. And so you're naturally going to see kind of overdensity of material here. So our galaxy is going to rotate, but the spiral structure isn't. So taking a look at this movie, if you look really close, you can see stars going in and out of the spiral, and that's the basic idea here. Now, in principle, both of these could be correct. They're not exclusive, and it's an active area of research, basically seeing are one or both of these theories supported. So what about the bulge at the center of the galaxy? If I have a big clump of gas that's forming, this is going to be the place where you have the highest concentration of matter, right? That's what's going to define the center that everything's orbiting, is you have a little bit more mass there than anywhere else. And so just by definition, there's going to be a lot of stuff there, and that's more or less all there is to say about the galactic bulge. Now, one issue with everything I just taught you is that there may be a problem, and this thing called the monolithic collapse model could be wrong to some extent. So the model I just mentioned is that you have a really large cloud of gas, it's going to break up, and then that's going to form smaller stuff. That's what we just covered. Now, there's a competing model of galaxy formation, and it's one, it's called by a lot of names, but one is multiple mergers. So instead, your initial large gas cloud actually breaks up into smaller clouds, and then these things are going to merge to form your galaxy. Now, why would I bother teaching you about the monolithic collapse model if it's maybe wrong? It's because all of the general processes I described in the past couple slides are basically the same, and the end result is the same. You're still going to have lots of collisions between gas. That's going to form a disk. You're still, by definition, going to have more stuff at the center. That's going to form the bulge. You still have these sort of winding processes, and this density wave theory could still explain a spiral structure. So none of that's technically wrong. It's just the question of whether or not you have a top-down kind of building or a bottom-up building process. And just frankly, we don't really know. Now, we do know that there have been collisions with our galaxy. So what we can do is look at stars out in the galaxy, and you'll see groupings that have different sort of chemical signatures. And by that I mean they'll have maybe a lot of metals compared to other stars, or maybe not a lot of metals. Remember that a metal is any element heavier than hydrogen for astronomy purposes. You don't need to know the details. The point is that you have these sort of chemical fingerprints, and you can see that certain groupings of stars are unique. They were formed at different times in different places, and they somehow now have come together. And the only way to really explain that would be a merger. And you can also see these groupings of like stars kind of stretch out in arc-like shapes over the galaxy known as streams. This would also have the convenient, not would, it does, conveniently explain the presence of the sort of puffier thick disk and of a galactic halo. So the thick disk, this is basically stars that have been kind of kicked out of the initial disk area because of mergers with other objects, or stars from a smaller thing merging into the galaxy. Not quite equilibrating into the thin disks. That could explain that. And then, stars that are left behind or objects that are further from the Milky Way and get closer, these can explain the halo. So if you want to look at what this kind of thing could look like, this movie here is really nice. So it's a simulation that's trying to reproduce, roughly what happened to the Milky Way about 10 billion years ago, inferring based on looking at these chemical signatures of stars and their different orbits around the center of the galaxy. So in this movie, the Milky Way 10 billion years ago is the blue stuff, and the red thing is a littler galaxy merging in with the Milky Way, and it would look something like this. So this is a accurate simulation, and you can see that the red stars in the end are spread out with some kind of pattern in terms of their spatial location and also their velocity, so the motion that they have. And so looking at current stellar distributions and stellar velocities, we know something like this happened, and many other mergers have happened to the Milky Way. And this ties into the ultimate fate of the Milky Way. This technically isn't formation, but if you're going to talk about formation, it seems like talking about the end makes sense too. So the nearest galaxy to us is one called Andromeda, and it's approaching us at around 100 kilometers per second. That's pretty fast. And we're on a collision course in about 4 billion years. The Milky Way and Andromeda are going to merge. And if you wanted to know what that might look like, there's this really cool reproduction that are done here on the bottom. And this is if you were on Earth and Earth maintained its position from the center of the Milky Way around 26,000 light years away. Okay, there's no guarantee that would happen. It very well could be flung away in the merger, but the night sky, out in the desert where it's very dark, would look something like this. So you have your Milky Way and Andromeda about 3.75 billion years from now. As these start to merge, you're going to have huge bursts of star formation, because when they merge, the gas in the galaxies that's not caught up in stars, that's going to become higher density just from the two things colliding, and so you're going to have this huge burst of star formation. The night sky would look like a fireworks show, basically, and that continues to happen, and then eventually in about 4 billion years, you can see that the two have kind of passed through each other. So the Andromeda galaxy has now kind of shot through the Milky Way. All of these stars that were in this nice, neat spiral pattern are going to just, because of all these gravitational interactions, get flung every which way, and instead you're going to have kind of these two orbs, one that was the Milky Way and one that was Andromeda, and this is eventually going to merge, and it would look, something like this. And the reason it looks like you're looking at a circle is we're assuming that we stay 26,000 light years from the center of originally the Milky Way. And that is how we believe that the galaxy as we know it is essentially going to end, and then you have some new other thing, this merged Andromeda Milky Way galaxy. And that is it for this introduction to Milky Way formation for Astronomy 1000.